Let's have a look at another question in electricity and magnetism. This one involves with electromagnetic induction in specific. Let's read the question. A long straight wire illustrated above carries a current I to the right. The current varies with time t according to the equation I equals I naught minus kt. So here k and I are both positive and remain to be positive throughout, which indirectly tells us that this equation I equal to I naught minus kt is in such a way that the value of current I decreases with increase in time. This is another way of saying I is inversely proportional to t. Next, the bottom of a rectangular loop of wire of width b and height a is located at a distance d above the long wire, with the long wire in the plane of the loop as shown. A light bulb with resistance R is connected in the loop. Express all algebraic answers in terms of the given quantities and the fundamental constants. Let's start answering the question. Indicate the direction of current in the loop, whether it is clockwise or anti-clockwise. Here we know that the current flowing through this long wire is decreasing with increasing time. Hence, the magnetic field B and hence also the flux that is produced by this current in the long wire will also change such that it decreases with increasing time. And we can use right-hand thumb rule to suggest that the direction of the induced magnetic field or the magnetic flux is out of the page. Since the current induced in the loop should be such that it opposes the changing magnetic flux given by Lenz's law, we also understand that the current in the loop should be such that it produces an increasing magnetic flux that is out of the page, so that it counters the decreasing magnetic flux that is produced out of the page, thereby reducing the changing flux to 0. So by this logic, we understand that the current in the loop should be induced in the counterclockwise direction. Moving ahead, indicate whether the light bulb gets brighter, gets dimmer, or stays the same brightness over the time period of interest. Here, I know that current I is decreasing per unit time, which means the flux produced by the current is also decreasing per unit time. Hence, the induced current is such that it produces a flux which is increasing per unit time. This being said, I know that EMF is not the increase in flux, rather it is the increase in flux per unit time, or mathematically speaking, it is the differential of the change in flux per unit time, albeit negative. Since I know that the flux is increasing uniformly, the rate of change of flux with respect to time is a constant, which in turn tells me that for option B, I understand that the voltage across the bulb or the EMF is going to remain a constant. I know that the resistance of the bulb is also going to remain a constant, which means power that is dissipated from the bulb, which is V square over R, is also a constant. Since power is a constant, the brightness also remains a constant or remains the same. Moving on to part C of the question. Part C asks us to find the magnetic field at time t equal to 0 due to the current in the long wire. I know from Ampere's law that I can write the equation phi B dl is equal to mu naught into I. I know that in general, any flux, whether electric or magnetic, can be written as flux is an integral of field into differential of area, or more so in general written as field into area. Field into area. This being said, I know that I can write this equation as the magnetic field strength B into area, which is equal to mu naught times I. This can be rewritten further as B is equal to mu naught into I divided by 2 pi r. But I also know that at time t equal to 0, the equation I is equal to I naught minus kt just becomes I naught since t is substituted as 0. Thus the final equation for B is equal to mu naught into I substituted as I naught divided by 2 pi r. Let's move on to the last part of the question. Derive an expression for magnetic flux through the loop as a function of time. I know that flux in general is differential of field with respect to area, which I will borrow and write here as flux phi b is equal to the integral of the field strength, which is B, into the area, which is dA. I know that magnetic field strength B can be substituted as mu naught into I divided by 2 pi r, which is what we derived in the penultimate part of answer to C. dA is a differential of area. I know that the area here in question is such that the width B remains a constant while the length varies from a distance of D as shown here to a distance of D plus A as shown here again. So the limits of my integration are pre-decided as D to D plus A, and dA, which is area, can be written as breadth B into differential of length dr, where r can vary from D to D plus A. Here r is indicative of length of this rectangular loop. I know that in this integration, mu naught is a constant, I, which is I naught minus kt, is a constant, 2 pi is a constant. So the only term within the integration is 1 by r dr for the limits d to d plus a. When simplified, I get mu naught. I can be substituted as I naught minus kt divided by 2 pi. I know that integral of 1 by x dx is ln of x. So here the ln of r is under the limits d plus a to d, or d to d plus a, sorry, which makes my simplification as ln of d plus a minus ln of a. And since ln a minus ln b is ln of a by b, this is what I end up with as my final expression. Here ln is just natural logarithms. So this concludes the answer to our given question.